Yo, what is up guys? I'm coming here at the beginning of the video just to give two quick disclaimers. The first one being that I'm gonna leave my mistakes throughout the video because everyone makes mistakes while coding, and the intention of this video is not showing how to perfectly code something. I'm showing how you can code your own data structure, and on top of that, I'm here to showcase how you can fix mistakes throughout your code. So this is how I deal with my bugs, problems with compilation and syntax errors. And the second disclaimer is that the txt I'm currently showing here is the final txt of methods that we've implemented throughout the video. And the at the beginning of the video, this txt doesn't have all these methods, and we're going to add a few of these methods throughout the video. That's why the video is quite long, because I initially thought that I would implement a few methods, and then I've added more methods throughout the video. So that's it. Enjoy the video. I hope you like it. See ya. Yo, what is up guys? So today I want to bring you guys a tutorial on how you can code your own linked list data structure using the C language. Okay, so if you've watched my previous videos on how to create your own stack and your own queue using the C programming language, you already know how to create your own linked list, because we are using the idea of a linked list data structure. But we were limiting the linked list data structure functionalities to wrap around the stack and the queue capabilities. So in a stack, we were doing a LIFO data structure, so last in, first out, and we had a few methods. And on the queue data structure, we had a FIFO, first in, first out data structure. So we basically have pretty similar methods between queue and stack, but the difference is in how you operate this linked list. And now we're gonna introduce a linked list, but without these limitations, and you'll have all the functionalities a queue had, a stack had, and with a few additional features that we're gonna implement here. So, as for example, we'll be able to check elements by a given index, and we're gonna be able to insert elements in a given index in the list that we were not able to do in the queue or the stack. So just recapping here, I'm just gonna showcase what a linked list will look like. So first, let me just grab here my pencil. So we always gonna have a node data structure. This will be our node, and in this implementation, our node has a value and it has a pointer. So this is a pointer, and a value holds the value we want to represent in our linked list in a given index, so to speak, and the pointer points to the next element in our linked list. Okay, so our next node in our linked list. So as I stated before, a linked list is different from an array, because when you have an array of elements, they are in a contiguous piece of memory. So one element is right after the other, and the difference between one address of memory from the other address of memory for the next index that is storing the next value is the size of the type you're storing in the array. So that's why array, you have the idea of indexes or indices that you can access by adding the size of the respective type you're storing here times the number of indexes you want to access. Okay, so different from an array, a linked list does not have this idea of a contiguous piece of memory and stores each node separately, and that's why we need pointers to the other nodes, because they can be anywhere in memory. They could be right after, but they could be anywhere in memory as well. So we need pointers to the next element, so we can actually track the elements we're storing in memory. So and usually the last element points to no, meaning that it points to nothing, meaning it is the only node in the linked list. So in this implementation of the linked list, as we did in the stack and as we did in the queue, we're also going to have a head element. So this will be our head element, because we'll have to initialize the queue, and we have a pointer pointing always to the head element. The head element will store a value, and this value here, value, and let me just write here, this is the head node. So we're always going to have a head node, a pointer to the head node, and the head node will store the value, and this value represents the number of elements within the linked list. Okay, LL stands for linked list, and the pointer of the head will point to the first element, but if we do not have any elements yet, this will point to null. So this is the standard structure when we're going to implement our init function. So we're going to initialize a node having the value 0 pointing to null, and we'll always have a pointer to this head node. And from here, we're going to be able to insert elements at the beginning, at the end, at a given index, and we're going to have to check if the list has enough elements so we can access that index. Otherwise, we're going to have an index error, and so forth. So that's how we're going to implement it. I've wrote here some methods that we're going to implement. So I also forgot here about the print linked list. I'm just going to print the linked list in a formatted way. This is basically going to be the same way we were using to print our queue and our stack. So if you watch those videos, you know how to implement this print linked list. And so let's first start creating our init linked list. As we stated here, we're going to create this structure here. So let's hop onto the code here real quick. So nvim linked list. Let's include the basic libraries again. So standard library and standard input output. As we always do, this is for printing, and the above one is for mainly for malloc in this case. So create our main function. Let's create our main function, returning 0 if everything is going fine, and let's create our linked list. We're gonna call it L list, or L like that, just to make our lives easier to not write linked list extensively every time we refer to it. And let's first create the data structure as we did in the previous tutorials. So this is going to be a type def struct that we're going to call a node, and our node has an integer value and it has a pointer. So let's create here a struct node pointer to the next node. So what we have here is an integer value. So this represents the first value, and we need a pointer to the next node. So that's what we're having here, our pointer called next that points to a node. So we're pointing to the next node, okay? And first thing we have to do is initiate the linked list. So it's passing our linked list, and let's create our function init linked list pointer. As I've stated in the previous tutorials, I'm using the pointer to the pointer reference here, so we can use a void function and we do not have to return a linked list object here, okay? So first thing we're going to do is, for readability, as always, let's instantiate a linked list pointer called list equals to the dereference of p, so we can use the term linked list throughout the whole function to make it a little bit easier to understand. And as always, when we instantiate something, we have to check if it is not already instantiated, and we do this by checking if it's not null. If linked list is pointing to something that is not null, is already initialized, so we're going to print to the user linked list has been already initialized, and an early return. Next up, we're going to initialize our linked list. So the way we're going to do this is we're going to create and allocate our first node. So we're going to allocate our first node and then make our pointer that is currently pointing to null point to this new node. So let's create a linked list pointer called temp for temp, short for temporary, and let's allocate memory for this size of linked list. So we are allocating memory for our first node for our linked list. And one thing I forgot here, this is called linked list. So this type def structure is called linked list. So we're allocating a first node for our linked list, and we have to check if the malloc did not return null, because if it did, it didn't work. So let's print to the user here malloc returned null in init linked list, and let's return if something didn't go as expected. And now from this point on, everything went okay, so our value will be 0 because this is our head node and we currently have 0 elements, and our next node will be pointing to null because we currently have no elements in the linked list, so that's why it's pointing to null, okay? And now we just get the reference of p to point to temp. And now let's create, as usual, our print linked list to make our visualizations of the current state of the list a lot easier. And we're going to pass in a linked list called linked list. As always, we're not going to pass a pointer to a pointer here because we're only reading the memory, not writing to it. So just passing the pointer as a reference here, we can read from it. So we also have to print only if it is initialized. And here we're checking if it's not, if it has been initialized, but we have to make sure that it is initialized. So if list is equal to null, we have to return to the user that it has not been initialized. List has not been initialized, has already been initialized. Just fix these typos real quick. So now that we are sure that this list is initialized, if the head node has 0 values, so if linked list value is equal to 0, this meaning that the linked list is empty, linked list is empty. So this is in the print linked list function. And now we return, and if it is not empty, we can iterate through all the elements and print them in sequence. So that's what we're going to do here. So while linked list next is different from null, we're going to print here the linked list element. Oh, sorry, we're going to print the value with a pointer. So this way, we're always going to print an element that has a next element via this value with this arrow symbolizing it points to some other node that has a value. So in here we're going to print the value, and on top of printing the value, we have to pass or to iterate to the next element. So our linked list will be our next element. And when we reach the last element, we just want to print it. So we're going to print the element without any pointers because it's not pointing to anything, it's pointing to null, it's the last element. And then we can print the linked list value here. Okay. So in order to test everything as usual, what we're going to do is we're going to instantiate or create the function declarations here at the top for both of our new functions here. So we're good, and let's add the print functionality here. Print linked list and pass the list. And now what we can do is we can compile it. CC linked list output linked list, and let's call linked list. So I forgot to add. It works as expected, but I forgot to add a break line at line 44 here. So let's clear, let's recompile it, and let's run it. So as expected, the first print is before we initialize the queue. So that's why it says here that linked list has not been initialized. And the second print is after we initialize the linked list, but it has 0 elements. So it prints that the list link is empty via the function print linked list here. So let's get back into the code. So that was what we were doing there. So printing before the initialization and printing after the initialization to test both of these cases. So the first one prints that it is not initialized, and the second one prints that it's empty. So we now have to add elements to the linked list. So first thing we're going to do is, as usual, we're going to create the add first, because we're going to add elements let's create the add last method first. So init linked list is okay, and what else? The print linked list is also okay. So let's now create the add last. So we're going to add an element, a given element, to the end of their linked list. So let's increase the font size a little bit. I guess it was not very easy to read. So now what we're going to do is create our void add last. We're going to call it linked list, pointer to our linked list, and an integer value we want to insert, right? So let's insert here at the end of the linked list. Every time we have to check if our linked list has been initialized and it is not null. So let's add it here. And now we're gonna add a new element. So as we're instantiating the linked list, we're allocating memory for a new node. We're gonna do the same thing here. So we're gonna allocate memory for a new node, but instead of the value being 0, the value will be the value we pass in by the function, and we'll point to null because in this case we're adding to the end, right? So here we also gonna have to loop through the end until we reach the end, and once we reach the end, we're just going to we're essentially doing is we're looping until we reach the last element, and we didn't have to print because it's just adding the element. Once we reach the end, we're going to add the new element at the end. So our linked list next, so this is currently our last element. We're going to say that the next of the last element now will be our new last element called temp, and we're going to also increase the head value, because as we stated, the head value holds the number of elements we have in the list. So if we're increasing the number of elements in the list, we have to increase the counter. So that's essentially what we're doing here. So add last is a pretty simple function. It's done. So we can test the add last here. So let's print adding to the end of the linked list, and let's print linked list, linked list, and we're gonna print it after we add last to the linked list, and we're gonna insert some values. So let's first insert some sequential values. Let's insert 1, 2, 3. So let's get here 1, 2, 3. So let's create a loop here real quick. So I guess this will be easier to do. So for int I equals 0, I is less than. So we're gonna insert 1, 2, 3. I is less than equal to 3. I plus plus. Let's add last, and we're gonna add to our linked list, and we're gonna also, or let's just get this line over here. So we're also gonna add the I plus 1 because we're gonna start by 1. Okay, so we're gonna add number 1, number 2, and number 3, and we're gonna print the list every time we add elements. And to check it out, we have to test it. So let me just create a function declaration for this add function here, and we can test it out. Let me clear this. Let me compile this. We have some compiling error. So linked list equals next. Linked list is a pointer to pointer. Let me check here what we got wrong. Oh yeah, this is not okay. So this is supposed to be P. And here we have a linked list called linked list. The reference is P. So let me clear it, recompile it, and we're passing by reference linked list. Print linked list from incompatible pointer type. Oh yeah. And right over here at line 23, on the print function, we only pass the linked list. We don't pass the address of linked list. So okay. So let's compile it. Let's run it. So as we've seen before, when we first print the linked list, when it's not initialized, it says it has not been initialized. Then we print after initialization, it says the list is empty, and we start adding elements to the list. So we have one element, number 1, then we have 2 elements, 1 and 2, and then 3 elements, 1, 2, 3. Okay, so everything is working fine. So let's get back into the file and mark here that our add last function is fine. Now what we're gonna do is add first. Okay, so we're gonna insert elements at the beginning of the linked list. And that's the advantage using a linked list over some other data structures when you need insertions at the beginning or at the middle, because in an array, so let me just draw it here real quick. If you were using an array, you would have to shift all the elements from one point to another because they're in a contiguous piece of memory, right? Let's get back this here. In a linked list, if this is our first element and it is pointing to the second element, number 1 for example, that is pointing to number 2. If you want to insert an element right here, it is pretty easy. So the only thing we have to do is change this pointer to point to this new element that we're going to create. Imagine we're inserting number 3 here, right? And make this point here. And that's all we have to do in a linked list. We only have to change one pointer, and that's it. That's all we have to do. But if you're trying to insert at the beginning of an array, imagine you have 0, 1, 2, and you want to insert number 3 here, right? Or in between number 0 and number 1, as we're doing here. So you want to insert number 3 here, right? What we have to do is basically you have to either create a copy of the array and simply copy the elements in order, so 0, 3, 1, and 2. So this is a copy of the array, and then you delete this array. Or what you would have to do is rearrange the elements in this array, and that is not something very easy. So you would have to shift 2 and then shift 1, and then this would still be 1, and you rewrite 1 with 3 here, okay? And you can do that at any given index. You would have to do one of these two operations, for example, using an array. So using a linked list, you just simply have to shift two pointers. Essentially, you shift one pointer and you create a new pointer to the element that is the next element, and that's all. So this is what we're going to do here to insert at the beginning. To insert at the end, what we did was we iterated through the whole list until we found the last element that's pointing to null, and we simply created a new element. The last element is now pointing to the new element, and this element is now pointing to null. That's what we done when we were inserting at the end, and this is what we're going to do when we're inserting at the beginning. So let's implement this function here real quick, called void add start, right? Is it start? Add first. One is add last. This is add first. So also going to have a linked list pointer and an integer value that we want to insert. And here we're going to copy a lot of stuff from this function. So check if the list is already instantiated. We're going to copy up to here, because it's essentially the same thing. We have to check if the list is already initialized, and we're going to create a new element. But instead of pointing to null, what we have to do is now this will point to the second element of the list, right? So this essentially will point to the linked list next, and then linked list next will point to this guy. And that's all we have to do. And of course, at the end, we have to increment the number of elements in the head, right? Increase the value of the head. So what we're essentially doing is we're creating a new node with the value given by the function, and we're pointing the next element of this new created node to the second element in the linked list, because we're inserting at the first position. So the first will now point to the second, that is currently the first, and then we're saying that our linked list will now point to this new element, and this will now become our first element, and that's all we have to do. Okay, so now let's create the function declaration for this add first function here. Let's insert things here, and now let's do the same loop, but instead of adding to the end of the linked list, we're now gonna add to the beginning of our linked list. So instead of being add last, this will be add start, right? Add first. I'm always forgetting about this. So add first. So we're gonna insert at the beginning, and now we're gonna insert numbers from 4 and beyond. So we start at 3 up to number 6. So 3, 4, and 5 will become now 4, 5, and 6. So here we're inserting 1, 2, and 3, and now we're gonna insert 4, 5, and 6. So here they were inserted in order, so that's why when we printed it was 1 pointing to 2 pointing to 3. Now we're gonna insert at the beginning, so now we're gonna have 6 pointing to 5 pointing to 4, and 4 pointing to 1 pointing to 2 pointing to 3. This is the expected behavior. So now let's clear this, recompile this, and run our linked list. So as expected, this is the behavior we're waiting. Let's just insert some print statements here in between to make our lives a little bit easier to read what is going on here. So I'm going to copy this, and now I'm going to paste it here. Instead of being at the end, now we're going to say that we're inserting element at the start of the linked list. Okay, so let's recompile this and run it. So this is what was happening before. It was okay, so we're inserting at the end, so 1, and then 2, and then 3. Now we're going to start inserting at the beginning, so that's why we have now 4 elements, 4 being the first one, pointing to 1, 2, 3. Now I have 5 elements, 5, 4, pointing to 1, 2, 3, and then now we have 6 elements, 6, 5, 4, 1, 2, 3. So the insertion at the end and insertion at the beginning is working as expected. So our add first is okay. So now let's try to implement our add index function. It's not okay yet, so we're gonna start implementing it yet. So let me save it real quick. Now let's get back into the file and implement our add index function. So in this function, we'll have the ability to pass our linked list as usual. The index, we want to insert the element, and the element we want to insert the value we want to insert, right? So as usual, we have to check a few things. First, we have to copy this because we're inserting a new value. Let me just copy this line and paste it here. And one thing I want to make correct here is this right here. Oh, it's down here. This is not init linked list. This is add first. And we also have to change here in add last. In add last. Okay. And this is in add index. Add index. So now, what we have to do is, on top of checking if the linked list is not initialized, we also have to check if we have enough indexes. So if our index value is actually feasible to insert. And that's pretty easy because our head element holds the number of elements inside the list, right? So assuming that we're going to insert indexes from 0 to n minus 1, meaning n being the number of elements within the array, we only have to check if index is less than, is obviously greater than 0, or greater than minus 1, or greater than or equal to 0. And we have to check if index is less than or equal to our, or less than our linked list value, because we now have a number of elements. If we have only one element, we can insert at index 0, right? And for example, let's say here that we have only one element. Let's draw here. It's a bit easier. So imagine we have our head. It has like 2 elements, right? And it's pointing to number 1 and number 2. Number 1 and number 2, okay? And this is pointing to null. So this is our zeroth index, and this is our first index, right? Because our head is not an index. It's only counting the number of elements we have. If we want to insert at the 0th index, we need to have at least one element, right? At least one element. If we want to insert at the 2nd index, we need to have at least 2 elements. So now, one thing we have to make sure is when we're stating that we want to insert at a certain index, we want to substitute this index via the new element. So say that we want to insert the number 3 again, so at index 0. So we're going to create a new node with number 3. We're going to point this guy to this node. So we have to change the pointer of the head to this guy. This guy will become index 0. And these 2 guys here will become index 1 and number 2. So when we pass in the index, we want to substitute the value that is in that index by this new value here, okay? And that's what we're doing. If we want to insert now at index number 2, what we have to do is we have to substitute this value, okay? So in order for us to substitute this value, we want to create a new value. Let's say we want to insert number 4. Now this will point to this guy, and the last element here will point to 4. And now this guy is 0, this guy is 1. Now this guy down here, number 4, is index 2, and this is index 3. Okay, so this is the logic we want to implement, right? And what we have to check is what happens when the linked list is empty, right? So if we have an empty linked list, this is pointing to null, right? So if this is pointing to null, meaning that the linked list is empty, we can only accept index 0. So we'll add at the beginning. So this is what we're going to do. So this function will behave when the linked list is empty. This function will behave as add first, as we just implemented. Okay. So let's code this. And first we have to check if the linked list has been initialized, and then we have to check if linked list next is equal to 0. If so, we're going to insert at the beginning, right? So if this is equal to 0, we're going to call our add first on p, and then we're going to return. And add first requires two arguments, the p and the value will be the same as we have here from the function, okay? And we're not going to use the index because if, and we have to check that if this is equal to 0 and the index passed by the user is equal to 0. So, and the index is equal to 0. Okay? If not, we have to notify the user. So, for example, now that the index is different from 0, for example, if he passed index 1 and the linked list is empty, we're going to check if the index is greater or equal to 0 and it's less than the linked list value. So now it's 0, so 1 is definitely not less than 0. So if this is the case, we're going to print to the user here, invalid index. Current linked list only has x values, x indexes. So here, our indexes will be our linked list value. So this is the head, right? We're still in the head. And the head counts from 0 to the number of elements we have. So if you have one element, this will be equals to -1. So let's create an if statement here. If linked list value is equal to 0, we're gonna return linked list value. So let's insert here linked list value. Else, we're gonna return the linked list value -1. Okay. So I'm not sure if this single line if is correct. I don't remember, but I guess it is. We can try this out once we finish this. So now the logic has been implemented. So next thing we want to do is actually insert the value at the possible index we can insert. So we're going to create or allocate memory for this new value, and we have to loop the linked list until we reach that element. So before we actually insert, what we have to do is while linked list next, or while, let's create a while loop because we're going to jump x or I indexes. So while, let's create a for loop, I guess, for int I equals to 0, while I is less than index. So if pass index 0 less than or equal to index, we're going to increment our element here, I. So if 0 will do one loop, if 1 will do 0 and then 1, and that's correct. So let's add here the ability to loop. So linked list will be equal to linked list next, right? Because we have the number of elements here. And once we reach here, we're going to do the same thing as our add last function here. Our add first. But in this case, this element now is pointing to the next index from index we've passed here, and we have to shift elements around. So the temp value will do the same thing as before. So now, imagine we want to insert at index 0. So now our linked list is at index 0. And now what we have to do is get this element and to point to the new node. And the new node will point to the linked list next, the current element we have, but next. It's quite confusing to explain it here without drawing, but let's do this. So we have our head that has 2 elements pointing to number 1 and pointing to number 2 here. Yes, it's easier to explain like this. And this is pointing to null. So say we want to insert at index 0. So we're going to rotate here a loop until we reach index 0. So this is going to happen only once. So now we have to replace, okay, the logic is a bit off. So we have to replace this element. So in order to do so, this will be less than index. So if we start at index 0, so if imagine we want to replace index 0, this will stay, the head won't change, so we will keep here. And now what we have to do is create a new node, number 3, that will point to this guy, and this guy will point to this guy. This pointer does not exist anymore. And so imagine here we're inserting at index 0. Our linked list is our head, so our temp value will be equal to value. Our temp next will be equal to the next element right here. And now our linked list next, so let's add it here. This is the line we're missing. Our linked list next will be equal to our temp. And that's all we had to do. And of course, as we're inserting elements, we are going to add 1 to the value of p here. And we can test things out, but before that, let me just get this and add the function declaration. Number 13, j, oh wait. And I guess we can check it. Now we're gonna know if the single line is working. So it's not working. So let me check the syntax real quick. Let me open the file here. So let's check it here. So I guess I was a little bit off. This is from other language syntax. So what we have to do is we have a condition. We check if this is true. So this first element here is the true part. So this is what happens when it's true. This is what happens when it's false. Okay. So now I guess we can compile it, and now we can run it. We didn't add anything, right? So let's come back here to the function, line 28. Let's copy this, and let's add to a certain index, right? And instead of adding in a loop, now I want to add in specific lines to check what will happen when we try to insert things, right? So let's add index. We're gonna have to pass the index. So now that our list has 6 elements, we have from 0 to 5. So if we try to insert at index number 3, what will happen is we'll have to replace the 4th number. So the 4th number from our current linked list will be 6 pointing to 5, pointing to 4, pointing to 1. So we're gonna place a number in between number 4 and number 1. So let's put number 7 here at index number 3, right? And the number I want to add is number 7, right? And then we're going to print the linked list. And let's check if it's working as we intended. Let's compile it. Let's run it and see if it works. So yes, it is currently working. So as you can see, as we expected before we run it, we are inserting. So our current linked list has 6 elements. Number 6 pointing to 5, pointing to 4, pointing to 1, pointing to 2, and pointing to 3. If you want to insert at index 3, so this is 0, 1, 2, 3. We want to substitute this number 1 by the new number 7. So 4 will point to 7 and 7 will point to 1. That's what happened here. Now we have 7 elements, and now our number 7 is in between number 4 and number 1. So let's try to insert an index that doesn't exist now. So now we have indexes from 0 to 6. Let's try to insert at index 7 and see if it is working as we expected. So let's copy these 2 lines and insert at index number 7 that doesn't exist yet in the list, and insert number 8. Let's see what's going to happen. So let's recompile it and run it. It did input at the end. This is pretty wild. It wasn't supposed to happen, right? Because let me check something real quick. This is not supposed to happen. We're not supposed to be able to insert at an index that doesn't exist. So this has to be greater than or equal to 0 and less than value. Go back here. So this gets the cases where it's an invalid index, right? And it has to be greater than or equal to value. So now we have 7 elements. We're trying to, let me check here if I'm doing something stupid. No, this is correct, right? I'm dumb. We have 7 elements, but wait. We have now 0 to 6, right? 0 to 6 indexes. There's no 7th element or 7th index. So it has to be greater than or equal. If it is greater than our value, so it's 7 minus 1, this is the same thing to greater than or equal, or, this is an or. Now we're good, okay? Debugging in real time here for you. So now it is fine. So now it is doing the expected behavior. So we're adding to the if index of the list. So third index is 0, 1, 2, 3, 7 in between 4 and 1. So this is 7 in between 4 and 1. And now we have 6 indexes from 0 to 6. And we're trying to add number 8 to the 8th index, or to the 7th index that doesn't exist. So that's why it says that invalid index, current linked list only has 6 indexes. And let's go back. Let's clear it. Let's go back to our code. So this is doing the expected behavior. Let's get here and try to insert another element in a given index. So I'll keep this error, and now I'll try to add to the 5th index. I'll add number 8 in the 5th index. So we have 6 pointing to 5, pointing to 4, pointing to 7, pointing to 1. And now we're gonna insert again in between 7 and 1, right? So let's recompile this and run it. So now we're inserting again. Oh wait, so 0, 1, 2, 3, 4, 5. Yes, so 5 is our number 2, and now we're going to insert 8 in between number 1 and number 2. So yeah, this is fine. This is working as expected. So our functions are looking pretty good. So we have all our add functions working as expected. So our add index is also working fine. So let's add here an OK. Save it. And now let's see what function we're going to implement next. So let's check the contains function here. It's pretty simple to implement. So this function returns true if the linked list has a given element. So this is pretty simple, right? We're just going to loop through the whole list, through the whole linked list, and we're going to find an element. If we don't find it, we just return false. Okay. So let's create a function called contains, but it will return a value, true or false. Let's return an integer for 0 or 1. 0 being false and 1 meaning true. So we're going to pass in a linked list, and now we just pass the linked list, and we need a value to search, int value, and this is pretty straightforward. So all we're going to do is just we're going to loop through the whole linked list while linked list value is different from value. We're going to say that linked list is equal to our linked list next element. Okay, and if we reach the end and we don't find it, the only thing we have to do is return -1, return 0 for false. And if linked list value is equal our value, we return 1. Otherwise, we're going to keep doing this. And if we find it, we return 1. If we don't find it, we return 0. And now we have to add the basic checks here, because we can only check this in initialized linked lists. And let's also, I'll add the option to verify if this is equal to 0, because we cannot do this on an empty linked list. Let's get here from an empty linked list. Where is it? Where we check it if it is equal to 0. On the print linked list, right here. So let's grab this piece of code, get back down here, paste it here, and we're good to go. So now we're checking if the linked list has been initialized, and if it is not empty. If so, we're gonna loop through the whole linked list searching for a value, and if we don't find it, we return 0. If we find it, we return 1. So let's go back here. Let's search the linked list. So let's add a line here, searching for elements. So contains, let's put here in parentheses, contains. So we're gonna call contains on, let's print here, printf, searching for number 8. So let's first search for number 8, contains linked list number 8, and another printf, we're searching for number 9 that is still not in the, hasn't been added to the list, contains linked list 9, and we have to print this, right? So let's copy this and add it right at the end here. This will return a value. Let's paste it here. Paste it right here. Oh, sorry. And this will return. So this should return number 1, and this should return number 0. Okay, so let's test it out. Before, let me just add the function declaration as always, so we don't forget it. Number 14, J, paste it. Go back. Let's compile it. Okay, we have typos right over here. Okay, this is fine. This is fine, and we're searching for 8 here, right? Let's clear this, recompile it, and we have more typos. Oh my god, what is this? Linked list. What? List. Linked list. Did we fix all the typos? No, we didn't. For some reason, I've added another one here. What is going on? Return 0. Expected token before. What is this? Line 47. Let's get here. Line 47. Okay, need a parenthesis here. And this, we'll have to delete this. What a mess this has become. What is this? Running return with no value. Oh, let's just go back here and vim linked list. And we also have to fix this return 0 and this return 0. Okay, let's clear it out. Now we can compile it, and now we can run it. Some typos, and we got a segfault core dumped. So searching for 8 return 0. Let's check it here. What happened? If linked list is null, we're going to say that the list has not been initialized. If it is equal to 0, meaning that the list is empty. Otherwise, we're going to loop until okay, while linked list is different from value, we're going to keep on looping until we reach next. But if we don't find it, or linked list next, I guess we can only say here until we reach the last element here. I was kind of dumb. Our linked list next is different from null. If we reach null, we'll reach the last element, and that's it. Let's clear it. Let's compile this. Let's run it. And okay, now it does the expected behavior. So searching for number 1 or searching for number 8 returns number 1 because it is in the list. Searching for number 9 returns 0 because number 9 is not in the list. Okay, and that's all we have it. So let's go back to the file. Let's just fix something. Let's just say okay here to the contains. Peek first and peek last are really easy to implement as well. So this will only return the first element, and this will return the last element. So let's just add it here to the end of the file. So peek first, so return integer. So peek first, linked list, and we're gonna do all these checks. Copy this, paste it right here, and at the end, we just have to return the linked list next value. Because the linked list here is pointing to the head, right? And the next is the first element, and we're returning the value of the first element on the list. So let's also copy this and paste it here. And this will be peek last. So the only thing we have to add is a loop that enables us to go to the end of the loop, or the end of the linked list, and we don't have to check anything, so we don't need this. We just have to go until we reach the last element, and then we return the last element. So we return the value of the last element, and that's it. So let's add these function declarations. 15 and this. Oops, sorry. Peek last and peek first, and now let's add it to the main function here. So what we have to do is peek first and peek last. So printf peeking first element, peeking first. Let's do this. Peeking first, we return an integer, and this will be peek first on our list, our linked list. And let's copy this line, paste it, and this will be peak last. Peak last. Okay, so this should work, no problems. Let's recompile this and run it. Oh, sorry. And run it. So, as we can see here, our peaking first and peak last are working fine. Let me just remove this second break line here to make it a little bit more easy to read both. Recompile this, run it. So, this is everything we've seen before. And now, peaking at the first element. So, our current list is 6, 5, 4, 7, 1, 8, 2, 3. The first element is number 6, that's why peak first return 6. And the last element is number 3, that's why peaking last return number 3. So this is also working. So let's peak first is fine and say that peak last is also fine. So we have implemented a lot of our current methods for our data structure. And index off is another pretty easy method to implement. We only have to return the index of the first occurrence of the specified element. So let's get back to the file. Let's implement here this function called index off. We pass in our linked list and the value we want to get from the linked list. We perform all these checks. Check if the linked list is empty, if it is initialized. And here, as we on the first occurrence, we just have to find the contains here. We'll do the same thing as the contains, but the main difference is that instead of returning 1, what we have to do is return the index. So in order for us to be able to return the index, we have to create a variable that will represent the index. We start at 0, and every time we loop, we're going to increase the index by 1. And if we don't find the element, meaning that we reach the end of the last element, it is not equal, we'll return 0. So one thing I've seen here is that if we're looking for the last element, so peak last, return last, for in the contains here, if we look for the last element, this will not return the last element because we're going until the next equals to null, right? No. It is right. We're going until the next is different from null. And once we reach the last element, we're not checking it, right? So if this value is different, is equal to null. So let's do this. We'll return 1, else we return 0. But I guess it's not good to use ternary operators here. Let's just return 1. If this is true, it's more readable, right? This is more readable format, at least in my opinion. So if we reach the last element, we have to check if it is equal to, instead of equal to null, this has to be equal to value. We're fine. And then we return 1 here. We also have to do the same check here in our index off. And here, let's check it again. So if our list value is equal to value, we're going to index plus plus, and we're going to return it, right? So this is everything we have to add. So let's just copy this, go to the beginning of the file, let's paste it in here, index off, and let's try to get the, let's also print the print queue again, or print list, linked list in this case. Let's print linked list, and let's peek or printf. We're indexing index off the number we're going to look for, index for of number 3. So we're looking for the last element, will be %t, and let's check here, index of linked list number 3, and let's copy this line, paste it, and now we're going to look for the index of number 7. Let's check how it is. Let me just again remove this break line. Let's clear it. Let's recompile this. Let's run it. So let's check it if it is working properly. So this is everything we've done so far. We've picked first and last, so we print the queue again. So this is our current queue. And index of number 3, it says it's 8. So this is 0, 1, 2, 3, 4, 5, 6, 7. So it's 7. And this is number 4, right? So 7 is number 4. 0, 1, 2, 3. We're returning one more than we should. So what we have to do is just check here what we're doing at the index of. It starts at 0. If it is equal, return. Otherwise, we sum. And then we go again. Why is it returning? Okay. So this is 0. Then next one is 1. So it should start at it should start at 0 because we find the element. If it is different from null, meaning that we reach the last element, our index should be this. So let's clear. Let's recompile this and run it. It's still returning number 8, right? That is pretty wild, right? Why? Index is 0. Now it's... Oh, okay, that is why. Because we're also counting the head on the searches, right? So if we're counting the head on the searches, this is not going to work. So what we have to do is we're going to say that our linked list is equal to our linked list of next. So we start searching always on the first element, and we also have to do this at our contains. So let's paste it here, and I guess we're good. So now this should work. Let's compile this, let's run it, and now it works as expected. So now index of 3 is number 7 and index of 7 is number 3. And now let's try to find an element that is not in the list. So for example, number 9. So let's go here. Let's copy this line and try to find number 9, or number 10 in this case, because we are already searching for number 9 up there. So let's compile this and run it. And index of 10 is 0. This shouldn't be returning 0. Where is it? Envin. So this shouldn't return 0. This should return -1. Okay. If it doesn't work, we should return -1 in this function, right? So let's say here it returns -1 if fails, and on contains it returns 1 if found, 0 if not found. Okay, so let's recompile this and run it. Now it does its job. So we found number 3 at index 7, so we have 8 elements, so 0 to 7, that's why 3 is on 7, and 7 at index 3, so 0, 0, 1, 2, 3. And index of 10, it doesn't exist, it's -1 because 10 is not currently in the linked list. So next up, we have to implement, so index of is okay, and last index of is pretty similar. So we're gonna pretty much use the same function. So let's go to the end of the file and create a new function called last index of. This will be pretty much the same thing, but this time we have to search for the last occurrence of an element, right? So let's say last index of. So right here, we have to save our last index equals to 0, and every time we find the element, we're going to set our index to the element, and once we reach the end, we're going to return it. So last index is equal to -1, and now we're not going to return index. If it is equal, we're going to say that our last index equals to index, So what we're essentially doing is, if we find the element, instead of returning, we're going to set our last index equal to index, and we're going to loop through the whole list and set last index equal to index, and we're going to always return last index here. So this is the only change we have to do. And for this, let's just add another element to the list right here. So printf adding two equal numbers. So we're going to add two number 11s. We're going to insert one number 11 at the beginning and one number 11 at the end. So let's add first to our linked list a number 11, and then add last to our linked list the number 11 as well. Now we're going to print linked list, print linked list, linked list, and now we have to check if we find the correct last element. So let's first test the index of. So this is printf index of 11. So this should return the first index of 11, meaning it will be index 0. So this should return 0. And we're going to return an index of linked list 11. And right here, we should just add the last index of. So last index of 11. And here is the last index of. Okay, let's get this. Get the function declaration, 18j, paste it, insert it, save it, and now we're gonna get the last index of this element, and this should be the number of elements in the queue minus 1. So this is the last, and this is the first occurrence. So let's clear the screen, let's recompile it. Last index undeclared, first used in this function. In the line 264, let's fix this typo, 264. Okay, this is an integer, right? We didn't declare the type. So let's check. This is everything we've done so far up to this -1. And we're gonna add two number 11s. So we have 10 elements now in the linked list. So number 11. So this is number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 elements. The first one being number 11, the last one being number 11, and the index of 11, or first occurrence of 11 is 0 because it's the first element, and the last index of 11 is number 9. So that's how we do it. If we added a number 11 at the middle here, it will always return the last one. Okay, so our last index of is always is also working. So let's go to the next one. Let's check here. Let's check the size, right? So let's check the size. The clear method. Have we implemented the clear? No, we haven't. So let's check the size. The size is pretty easy. So it's clear here. Let's get back to the file. Now at the end here, let's implement the size. Int size linked list. Linked list. The only thing we have to do is return the number of elements from our head, and this is the only check we have to do is if the linked list is not uninitiated, and then we just return the linked list value because it is pointing to the head, and that's how it does. So let's get the size. Function declaration. And let's print here the size. Printf size of list. And this is done just by getting here so let's get here size of linked list. And let's just implement the clear function as well. So let's just testify the size. So the size is 10, right? Because we're just returning this number. Okay, it works. Let's get back to the file. Now let's create the clear function. And before we create the clear function, let's create the remove. We have to create some remove functions here. So first thing we're going to create is the remove first. So it removes the first element. And then the remove last. So it removes the last element. Removes last element. And we're going to use it to implement our clear function. Save it. So let's implement our void remove first. That's in our linked list. And we don't have to pass anything because we're removing the first element. Let's get some checks here. Let's get from some function we already have here, like the print function. So let's get this, copy this, get to the end of file, and linked list is equal to pointer here, so the dereference of the pointer. So we're checking if the list is uninitialized, checking again if the list is not empty, and then we're going to remove the first element. And in order to do so, it's pretty simple. So we have our linked list here. With our head, say we have two elements, number 1 and number 2, number 1 and number 2, pointing to null. We want to remove the first element. We just have to check if the list is not empty, as we just did, and then we're just going to point the next, or the head pointer, the head node pointer to the second element, and remove this guy, point a temporary variable to the first element, and then free this memory, and that's all we have to do to remove first. So in order to do so, let's create a linked list pointer called temp that will point to the linked list next. So this is the first element, and our linked list next, we need that this will be our new first element, will be the second element, and then we free temp. And we also have to remove the temp variable. As we remove the temp variable, we have to decrease the number of elements within the list, so the p-value decreases here. And that's all we have to do to this function. And let's also implement the remove last on our linked list pointer. We're going to do all of these checks. Let's copy everything real quick. Let's paste it. Checking if the list is initialized and checking if it's not empty. Now we have to reach the end of the list. So while we have to reach almost the end of the list, because the list needs to have at least one element. So while the linked list next is different from null. So in this case, what we're doing here to remove the last element is we have our head node, 2 elements, the number 1 pointing to number 2. And as we want to remove this element, we have to, if we reach this element, if we get to this last element, we cannot change the reference from this element to null, right? So if we free this element, we cannot change this reference to null. This will be pointing to an unallocated piece of memory. This will cause a segfault. So that's why we, instead of going to the last element, we're going to loop until we reach this second to last element, and then we're going to point a temporary variable to this guy, free this memory, and set this to null. Okay, so that's what we're doing here. We're looping until we find the second to last element, and linked list next. Linked list equals to linked list next. And once we reach it, we're going to create a temporary variable that points to the next element, and our linked list next will now point to null. And then we're going to free the memory from temp. So this temp is pointing to this guy, and linked list next now is pointing to null. And we're going to decrease the number of elements in the list. So these are the two functions, the two main remove functions. And let's get to the end of the file. 21. Let's save it, and let's just add here these functions. So printf, removing from the start. So remove first, right? So remove first, we pass in the linked list, and then removing from the end. This is the remove last, and this is linked list, and we have to print q in between to check the q state. print linked list. I'm sticking with Q in my head for some reason. Let's try it out. Let's compile this. Let's run it. And this is all we've done so far up to the size. And once we remove from the start, the linked list was 11. 11 was the first element. So once we remove from the start, the first element has to be 6, and the count of element has to go down by 1. So now we have 9 elements, and the first element is number 6. And once we remove from the end, the last element was number 11. Now it has to be number 3. That's why we have number 3 here, and the number of elements in the list went down back to 8. So it's working properly. Now let's try to remove by index, and let's try to remove number 4 by index. So this is numbers index 0, index 1, index 2. So let's create a function called remove. So let's say that this is okay, and this is also okay. And let's create remove index, removes an element on a given index. So let's mark it as okay, because we'll do it right now. Sorry. So this is very similar to our function of insert index. So remove index, linked list, and we have to pass the index we want to remove, right? Index or int index. So let's get to the function called add index, and let's copy a lot of this function. So basically, we're gonna copy everything up to here, because these are all the checks we need. Let's paste it in here. Oh, sorry. What happened here? Okay, I don't know what happened, but space here. Now we have all the checks we need for this remove index function, meaning that we're always checking for the indexes that are possible. And now that we have to remove the element index, instead of going until we reach the index, we're gonna do the same thing. We're gonna loop until we find the last element before the index. So let me draw here. So imagine this is index 0. This is index 0, and this is index 1. If we want to remove the index 0, what we have to do is loop until the last element of index 0. So we wouldn't loop at all. We would stay here, and then we would say that the next element of this element we're current at will be the next of this index element. And then we're gonna point a temporary variable to this guy and free this variable, and that's all you have to do. Okay. So in order for us to do so, this loops until we find the second to last element given a certain index, and from here we're gonna say that we're gonna create a linked list pointer called temp. This will be pointing to our linked list next, and our linked list next we will point into the next from this guy. And then we free this guy, and after we free this guy, we have to remove the number of elements we currently have in our linked list. So remove the value of p value, and that's all. 20k. Let's add the function declaration as well, and let's test it out. We first have to add it to the file, right? So let's print here, print removing index 2, and let's check it out. Print linked list, and now we have to remove index. We're going to pass in our linked list, our index. We're going to remove. This is index number 2, and the value. We don't need to insert anything, right? So this is this function at the end. Remove index. We just pass in the index, right? So okay, this is fine. Let's just check something real quick. Removing index 2. That's all we have to do. So let's compile this. Remove index. Oh, we forgot a comma or semicolon. Where is it? We forgot a semicolon at the end of this line. Let's clear it, compile it. P value, add first, value undeclared, line 345. Let's go back. 345. Okay. Ah, okay. So instead of add first here, we have to remove first. Once we have this value here, we just remove first. It's the same thing as removing the first element. So let's clear it, compile it, remove first p value, and of course, remove first does not get any value. So let's get d back and compile it, run it. So let's see if this makes any sense. So up to here is what we've done. We remove from the start, so remove 11. Now we have left with 9 elements. Remove from the end, we remove the 11 from the end, so we're left with 8 elements. And now we remove index 2 from this, so this is 0, 1, 2, so that is correct. So number 4 is not here anymore, so 5 points to 7, so this is what happens here, 5 points to 7, and now we have only 7 elements. So our remove index function is also okay. Clear function is pretty easy. So clear function is, as we've done before, it's just a loop from remove first. So let's say that this will be okay because we're going to implement it right now. Clear. Let's get back here to the. So print linked list is fine. We're almost done with all the methods, and we only need to implement now the clear method and the free linked list method. They're pretty similar. So let's try to do this right now. So let's void clear function. We're going to pass in our linked list pointer, and all this does is while. So let's do here a linked list pointer, pointing to the dereference of b again, and while linked list is not null, does not point to null. Next is different from null. What we're going to do is we're going to remove first from our key. And we don't have to do any checks before this guy because let me just check something. If we call clear here on this function and this is pointing to null, linked list will be null and doesn't have any next variable, right? So let's just make sure that this is initialized. So this is an initialized list. I guess we didn't do this in the codes we've done before, but it has to be at least initialized. So if it is initialized, we can clear the whole list. So let's test this method. Let's go back here to the end of this file. Let's paste it here. Oh, this is the function declaration. Sorry. Let's add it here first. The function declaration. Let's get to the end of the function. Let's print f, and this will be printing clearing the linked list. Call clear on the linked list, and then we print linked list, and that's it. So let's check it. Let's compile it. Error linked list undeclared. So let's just make sure we. Okay, this is not supposed to be here. This is supposed to be here. So let's recompile it. Let's run it. And this is all we've done up to here. So once we clear the list, it has to print that the linked list is empty. So this is what it's doing. So clearing the linked list is working fine. And last but not least, we have to free linked list. And in order to do so, we have to create a function. Let's clear this. We only have to create our last function, void clear our free linked list. We're going to call linked list pointer, and same thing happens here. But do we have to do this? Yes, we do. So let's just check this if the linked list is initialized, because if we don't do this, we might be able to double free, and that's not what we want to do. And if the linked list has been initialized, we can now safely clear, and we're going to remove all the elements before. We simply remove we simply removed all the elements, and now we have to free the head of the queue. And in order to do so, we have to call free on our linked list, or in this case, our linked list is pointing to our head, and now we're called p. So if we call free on our linked list that is pointing to the head node, the last thing we have to do is say that our p now points to null, and we're done. And let's go back to the start of the file. Oh wait, let's just get this for the function declaration, number 24, and let's get down to so we can free. So printf freeing the linked list. And before we free the linked list, I want to add some elements. So let's add a few more elements where I can do it. Let's use the add list function here. So where is it? Let's create a loop here as we did at the beginning. Where is it? Okay, there you go. Let's get this loop. Let's add some elements to the list just to test if the clear function is working properly. Printf, adding some more elements to the list before we free it. That's essentially what we're doing here. So let's add like 5 elements from 0 to 4. So 1 to 4, 1 to 5. So 1, 2, 3, 4, 5. And then when we free the list, so free linked list. On our linked list, we can call the print linked list function as well on our linked list, and this now has to return, has to print that the linked list hasn't been initialized yet because we're freeing the head of the linked list. So what we're essentially doing is we're recursively calling the remove function or remove beginning. So we remove this element, this points to this, and now this removes to this, and this points to null. So this is what the clear function does. And the free, on top of clearing all the elements from the queue, this will also free this memory from our head. So this is what we're doing here at the end, and that's why once we clear the head, our initial pointer is pointing to null, meaning that it doesn't point to any piece of memory, and we're back to the uninitialized linked list. So let's get back here. Let's clear this. Let's compile it. And no, okay. Let's see where I've added this /z. This is supposed to be /n. Let's compile it. Let's run it. And yeah, that's it. So everything we've done up to down here, we've tested before. Now we're adding back elements to the queue. So we have 5 elements, 1, 2, 3, 4, 5, as expected. And once we free the linked list, we clear every element, and then we free the head, and the linked list has not been initialized. So just to recap, so we've created a bunch of functions here. So everything has been done. You can add more methods to your linked list as you'd like. You can insert only elements via insertion, ordered insertion. This is a special linked list, so a linked list will always be ordered, and that's a challenge that you can implement. But for this simple linked list we've implemented here, it has pretty good amount of methods. I guess you can learn a lot from watching this video. I hope you enjoyed it, and yeah, thanks for watching. So before we move on, let's just recap. So we're printing an uninitialized linked list, and then we're initializing and print it because it's empty. Then we add elements to the linked list at the end, so that's why it's 1 and then 2 and then 3. And this is always the number of elements in the list. And then we start adding elements at the beginning, so we add 4 and then 5 and then 6. That's why it's in this structure: 6, 5, 4, 1, 2, 3. Then we add elements to the ith index. So in this case, it's the 0, 1, 2, 3. So 0, 1, 2, 3. The third index, we insert number 7. And when we try to insert an element above the number of indexes we have, it says the current linked list only has 6 indexes. We're trying to insert at index 7, so that's why it only shows here that it only has 6 indexes and it doesn't do anything to the list. And then we try to insert into an existing index. So in this case, it's 0, 1, 2, 3, 4, 5. So at the 5th index, that's why we put number 8 in between number 1 and number 2. Now we search for elements number 8. Vi contains, and it returns 1 because it is in the current linked list. And when we try to search for number 9, it returns 0 because it doesn't exist in the linked list. We pick at the current linked list and it returns 6 because we pick first, so the first element is 6. When we pick last, it returns 3 because it is the last element. When we try to search index of number 3, it returns number 7 because index of returns the index of the first element in the linked list. So index of 3 is 7 because it is the last element from 0 to 7. And index of number 7 is at third index, 0, 1, 2, 3. And when we try to get the index of number 10 that is not in the linked list, it returns -1. So when we insert two elements, one that are equal, number 11, at the start and at the end, index of returns the first index, so it returns 0 because it is the first element, and last index of returns the last index of an element, so that's why it doesn't return 0 because there's another 11 and this is the last 11 on the linked list at the index 9. The size function only returns the number of elements in the linked list, so that's why it returns 10 because we have 10 elements. And once we remove from the start, the first element is 11, that's why the next element is 6 now, because we removed 11 and we reduced the number of elements in the queue. When we remove from the end, we're just removing number 11 here from the end, and now the last element is number 3, and we decrease the number of elements in the queue. And once we try to remove index number 2 from this current linked list, so 0, 1, 2, we're essentially removing number 4, and we're saying that now 5 points to 7, and 4 doesn't exist. This is what happens here, and we decrease the number of elements in the queue. When we clear the linked list, when we clear the linked list, we remove all the elements from the linked list, and when we print it, it says it is empty. Then we add some more elements to test the free. So we add number 1, number 2, number 3, number 4, and number 5. So we end up with 5 elements. And when we free the linked list, it removes all the elements and also frees the head. So that's why when we print it after free, it says the linked list has not been initialized. So that's a big recap. This was a very extensive video, very tiring video to watch, and a very tiring video to make, but it's pretty good to understand the different methods you can have on a linked list. You could add different methods to your linked list. You can make your linked list have specific methods. You can create your own modifications. So this is all I wanted to share with you guys today. Thanks for watching. If you have any questions, you can post on the comments down below. I'll try to answer them. And in the future, I'll bring a different data structures as I've been bringing you guys this last few days. We've brought to you the queue, the stack, and the linked list, and all these implementations involve linked list. I'll try to bring some implementations of different algorithms or data structures that are a bit different from what we've brought to the channel up to now. But that's all. Thanks a lot for watching, and I'll see you guys on the next video.